You think energy is just a number in a textbook. It's not. It's currency. Every fuel, every explosion, every power plant runs on one question. How many grams produce how many kilojoules? That delta H value, that's the exchange rate between matter and power. Cities don't run on opinions, they run on gram to heat calculations. If you miscalculate the energy output of fuel, you don't lose points, you lose power. This isn't just extra math, this is learning how to measure power, and leaders will always measure what matters. In this video, we're going to look at mass to heat stoichiometry, where we are focusing on two-step conversions. By now, hopefully you've already done one-step conversions where you've learned how to use delta H as a conversion factor with a mole ratio. So now it's time to actually begin to convert using the conversion factors of both the thermal heat ratio and the molar mass. So in this example problem, it reads, how much energy will be released, keyword right there, when 66.44 grams of sulfur react with excess oxygen with the following equation. So here are all the keywords that we need right here. Because this is released, this is negative delta H, so we expect the answer to be negative. And then we're starting with grams of sulfur. That means 1 mole of sulfur, S8, is equal to negative 6,331.2 kilojoules. But then the other factor that we need is the molar mass of sulfur, S8. So the molar mass of sulfur is equal to 256 grams per mole. Now that we have that information, we can start our problem. 6.44 grams of sulfur. Because we're starting with grams, we need to use the molar mass to cancel out the grams. So 1 mole of S8 over 256 grams. All right, remember we are burying the gram, canceling out the grams so we can give life to the moles of S8. Then we can use the thermal ratio between sulfur and the kilojoules, where heat energy of that is released. Because I want energy to be a part of the final answer, I need to put that ratio on top. And the mole, the 1 mole of S8 on the bottom. So the 1 mole of S8 will cancel out. And so the total amount of energy that is produced will be 6.44 times the negative 6,331 divided by 256. And you will get approximately 159 kilojoules of energy from 6.44 grams of sulfur reacting. So this is a demonstration of what it means to go to start with the mass and to convert the mass of a substance to the amount of heat generated in that reaction based on that mass. And then just in case you need it, here's the cleaned up version of all the work that had to be done. And you can pause the video as needed if you need to verify the work that you were doing in the problem. Rocket fuel doesn't care how confident you feel. It cares about ratios. Hydrazine, ethane, hydrogen. If you miscalculate the heat released per gram, the rocket doesn't almost work. It fails. Engineers often calculate exactly how many grams produce exactly how many kilojoules. Too much heat, you get structural failure. Too little, and you get no thrust. Gram to heat conversions are how we prevent disasters. You're not just learning thermochemistry, you're learning how to control energy instead of being controlled by it. That's how you take ownership in science. Now let's do a problem going backwards. We're going from heat to mass. So we know how much heat is generated, but we need to find out how much mass of a chemical is actually burned in that process. So it says calculate the mass, so the final answer has to be in mass, which must be burned in order to produce. So because it says produce 100 kilojoules of heat, again, we want to make sure that this is negative. All right. Produce energy as a product is negative. All right. So when we set up our thermal ratios, and our conversion factors. Let's go ahead and start with our ratio of ethane. So that means we have 2 C2H6 is equal to negative 3,120 kilojoules. And then because of that, we also need the molar mass of ethane. So the molar mass of ethane, C2H6, 2 times 12 is 24, plus 6, that's a mass of 30 grams per mole. So now let's begin to set up the problem. We're going to go ahead and put in our 100 kilojoules of heat. And because we're starting with kilojoules, we need to be able to cancel out the kilojoules of energy using the thermal ratio. We're going to take our thermal ratio and make sure that kilojoules is on the bottom because we want to get rid of that. We're going to bury the energy that is being released. And we're going to put the molar ratio part, C2H6, on the top. Before I move on, I want to make sure I backtrack because we said that the energy produced is negative, and I didn't do that at the beginning. So it is a negative 100 kilojoules. All right, so now that we have successfully canceled out kilojoules, we now need to convert to the grams of C2H6. So our grams of C2H6, that means 30 grams needs to go on the top, and 1 mole needs to go on the bottom. So that means the answer to this problem is negative 100 times 2 times 30 divided by 3,120. And as a final answer, you should get 1.92 grams of C2H6. I would show you the cleaned up version, but I realized that I made a mistake on the slides. So I'm going to leave it in this format for you to figure out. But these are the types of problems you should be working on. And again, these are 2-step. And remember, the challenge of the 2-step is you have to pay attention to what variable you're starting with so that you're canceling out consecutively. If you're not paying attention, you won't know where to start on a 2-step conversion and how to finish it. That's the challenge of the 2-step conversion again. So I advise you that if you're struggling with the 2-step conversions, spend time identifying the units. Don't skip any work. Don't skip any units, because the units are helping you figure out if you're doing the problem correctly. This ends in grams, this ends in grams. Stay consistent. And of course, as always, once you have seen these examples and you're confident of the work that you're doing, you are now free to pursue academic prosperity. And I'll see you on the other side of success.